Mm, hello.
Hey everyone, welcome back, and let's write some more neat code today. So today we're going to solve lowest common ancestor of a binary search tree. And if you recall, a while ago in a video I showed you guys this sheet of the 75 blind problems that have become pretty popular. And so this is basically a spreadsheet that I showed with an entire list of those problems, and I've actually ended up making videos for most of these problems so far. The video that we're doing today is actually going to be lowest common ancestor, one of the few problems that I haven't done yet. So I will be linking this sheet in the description if you do want to take a look, and I'll probably be trying to wrap up most of the problems in this list. I think one of the next ones that I'm going to be doing is alien dictionary because I really like that problem. And once I've gotten this entire sheet of problems done, I'll probably be making a playlist for it. But for now, you can watch the videos that are currently available for this list of problems. So in this problem, we're given a binary search tree, and we are supposed to find the lowest common ancestor of two given input nodes in the binary search tree. And so the lowest common ancestor is basically defined as being the lowest node in the tree such that P and Q are descendants of this node, or P or Q happens to be equal to this node. So basically, what we're saying is 6 can technically be a descendant of itself. So for example, in this example, we're given P equals 2, Q equals 8. So we're going to start at the root because the root is always going to be a common ancestor of every single node in the tree, right? That's just kind of basic, right? For this node and this node, of course, this is going to be a common ancestor. It's not necessarily the lowest common ancestor, but it is a common ancestor. So what we're going to see is P is less than 6. Therefore, it's going to be in the left subtree, and it actually happens to be a direct child of 6. 8 happens to be greater than 6, so it's going to go in the right subtree. So basically, if we went in the left subtree, 2, is 2 going to be a ancestor of 2 and 8? Of course not, right? 2 can't be an ancestor of the node 8 if it's in a different subtree. Similarly, 8 is not going to be a common ancestor of 2, so basically if we look at this level or if we keep going down, we're never going to find a common ancestor between 2 and 8, so the lowest one that we found ended up being 6. So we notice if there's a split between the nodes that P and Q are going at, if they're going in separate subtrees, where that split occurs is every ancestor. It's not necessarily the lowest common ancestor, but it is a of itself. So for example, in this example, node in the tree, right? That C is P is less than 6. Therefore, it's going to be in the left subtree, and it actually happens to be a direct child of 6. 8 happens to be greater than 6, so it's going to go in the right subtree. So basically, if we went in the left subtree, 2, is 2 going to be a ancestor of 2 and 8? Of course not, right? 2 can't be an ancestor of the node 8 if it's in a different subtree. Similarly, 8 is not going to be a common ancestor of 2, so basically if we look at this level or if we keep going down, we're never going to find a common ancestor between 2 and 8, so the lowest one that we found ended up being 6. So we notice if there's a split between the nodes that P and Q are going at, if they're going in separate subtrees, where that split occurs is going to be the lowest common ancestor. So if I change this problem slightly and I gave P as 7 and Q as 9, we would once again start at the root because we know this is going to be a common ancestor of these two nodes. And so now we're going to check, okay, 7 is greater than 6, right? And 9 is also greater than 6. So therefore, we don't need to search in separate subtrees. We can just go to the right subtree to look for both of these values. We know that this is not going to be the lowest common ancestor. This could potentially, though, be the lowest common ancestor. So now, once again, we're going to repeat that. We're going to say 7, that's going to be less than 8. So for a 7, we're going to have to look in the left subtree. 9 is greater than 8, so for that, we're going to have to look in the right subtree. So since this is where the split occurred, that means this is going to be the lowest common ancestor for this input. So we would return this node as the lowest common ancestor. So one last case is if we changed Q to be a 6. So once again, we would start at the root, right? Before we were checking if P and Q were both greater than 6, then we look in the right subtree. If they're both less than 6, then we look in the left subtree. If one of them is in the right subtree and one of them is in the left subtree, that's how we know this is the lowest common ancestor. But what about the last edge case where one of these nodes happens to be equal to the root node? In that case, this is potentially the lowest common ancestor. It's definitely a common ancestor of both of these, but now if we go lower, for sure none of the descendants of this node, nothing in the left subtree or in the right subtree is going to be an ancestor of this node itself, right? So basically, if we ever reach the node itself, for example 6, then that's going to be the lowest common ancestor. So it's an ancestor of itself, and it's also an ancestor of 7, which can be found down here, right? So this problem isn't too difficult once you can kind of understand that if there's a split between these two nodes, then that's going to be the LCA, the lowest common ancestor. And since we're doing it this way, we don't have to visit every single node in the entire tree. So the time complexity is not going to be big O of n, it's going to be log n, because we're only going to have to visit one node for every single level in the tree. So basically the time complexity is the height of the tree, which is usually going to be log n. And the memory complexity is just going to be big O of 1 because we're not really needing any data structures or anything like that. That being said, let's jump into the code now. So as I mentioned, we are going to start ourselves at the root node, and we're basically going to continue until we find our result. So we're guaranteed to find a result. P and Q are guaranteed to exist in the input tree. So what we're just going to say is while current is not null. Now it's never going to be null because we are going to find a result, but this is just a way to get it to execute forever until we find that result. So one case would be if the p-value ends and the q value were both greater than the root value or the current value. Value that we're visiting, and in that case we would have to go down the right subtree. So since we're going down the right subtree, we can update our current pointer to current.right. Now the else case is basically going to be the opposite of this, so I'm just going to copy and paste that. Basically, if both of the values happen to be less than the current node that we're visiting, in that case we would want to go down the left subtree, so in that case we can update current and set it equal to current.left. Now the last case is basically if our split occurs or if we end up actually finding one of the values P or Q. And in that case, it basically means we have found our result either way, so we would just be able to return current itself. Now, we don't have to put any return statement outside of the loop because we're guaranteed that this is going to execute at some point. So as you can see, this is a pretty efficient solution. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot.